we do some derivation from this particular antenna. Okay, so this is the example as I mentioned to you on Wednesday, on Sunday before. Okay, so different, and then actually if you can see the log periodic, actually it is what we can say that here log periodic antenna is the antenna which the electrical properties repeated periodically. Electrical properties repeated periodically with the logarithmic of the frequency. So this one also can sometimes called frequency independence. Okay, so this is an example of the log periodic. Okay, I will try to see later on. Okay, in terms of this, how we want to get the alpha, how we want to get the R tau for the dipole types of antenna here. So we are looking in terms of the log periodic dipole types of antenna here. Okay, so this is an example. You can see that this is the dipole antenna, straight connection, crisscross, and as well as the coaxial connection. So you can have different connections as well. Okay, so this is the log periodic dipole array. As you can see that the most important thing here is your tau here. So tau is actually is your scaling factor. How we got the tau here? So tau here actually is a scaling factor. Okay, L is the length, R is the distance from the apex, D is the distance, this is the spacing. So the spacing factor also can be, I will show to you how we get the spacing factor before. And then this is a log periodic dipole array, most commonly used for VHF, also UHF, capable of constant gain and input it over the bandwidth of 30, you see. So the bandwidth can be 30 up to 1. Gain of roughly about this. Okay, so if you want to design, sometime we need to use some on what we call the data or the graph that is being given. So maybe you can use it to design a certain band or certain frequency that you need to find out. Okay, it's about this. Okay, so I will show it to you in terms of this. Okay, right. Okay, so let's say this is your log periodic dipole. So this is your coaxial. Maybe we put it in terms of the crisscross here. It doesn't matter crisscross or not. Straight. Okay, so this is an example of your dipole. So you have this one, you have this one. Dipole here, and then dipole here as well. Okay, so this is the log periodic dipole antenna. Or maybe if we can make a bit more bigger here, so that you can have a better understanding. Okay, so let's say we move like this. So I put in terms of the crisscross here. Let's say this is your dipole. Okay, so this is the dipole types of log periodic antenna here. Okay, so as you can see that, what we can see that this is the apex angle. So this is at the center here. So that means you excite, okay, throughout this cable here, the signal, for example. And you can see that this is your coaxial cables throughout the transmission lines here. So for example, this is your R. So this is your R1 here. So sorry, this is your R. Let's say for example from this apex here we know that, okay, so we want to see that this is the alpha here. So this is the angle, we call this one is the angle of or apex angle here, alpha here. So this is your alpha actually, and this is the distance from here. We can say that this is Rn, and maybe this one is Rn plus 1. For example, is R1 is gitu, Rn is to 1, R1, R2, R3, and so on. And as well, you can see that we have in terms of Ln here. So this is your Ln plus 1. Okay, so it's better to put here like. So this is your Rn plus 1. This is your R1. So this is your R2. So we can see that, okay. So this one is Rn. This one is Rm plus 1. Okay, so the example. And also, we also have in terms of what we call here is a spacing here. The spacing here S. Spacing is S. Or we can say that this is in terms of S here. And also sometimes, you know, in terms of the tube as well, you should know as well. So let's say we want to find out. So what we can see that, as you can see that we have the L here. L2 over L1 should be equal to L3 over L1 plus equal to dot dot dot. So maybe you have L3 over L2, sorry. So what we can see that here, LP, this is the log periodic dipole antenna. So we have in terms of side by side. So it means that side by side here and here. So side by side, okay, like this. So there's a side by side, parallel dipole, okay, and then ends meets to form the angle alpha. Okay, so now we want to find what is the value of this alpha and this. So what we can also say that all dimensions is increased in a proportion to the distance from the region. So we have one particular thing that we need to define here is tau. Tau is actually is your scaling factor, is Rn over Rn plus 1. So usually for this kind of log periodic, we can say that we have tau, it should be less than 1. Less than 1. So if you look in terms of the impedance versus the frequency here, for example, so this so what you can see that you have a stable impedance here like this. So this is an example of this particular log period. And in terms of the log period as well, we can see that we have in terms of 3 regions here. Okay, so we have 3 regions. Okay, for example, this is the inactive region we call. Okay, this one maybe is the active region. And this one is the reflective region. Okay, so in what we can see that here in log periodic type photon, we have 3 different regions that we need to define throughout this log periodic dipole antenna. Okay, what can we say about these 3 regions here? Okay, first of all, what we can say in terms of the region, so we have inactive region. It can be defined when your L is less than, sorry, L is less than lambda over 2. Okay, so it means that, as you know, that the dipole antenna, the length is half wavelength. So when you have L is less than lambda over 2, so this is called the inactive regions. So what we can see as well, so elements here, what we have here, elements, presence, high capacitive because of L is less than capacitive impedance, less than half wavelength. Okay, and then element current is small. Okay, so this is what we call the inactive regions here. And then if you talk about the active regions, what is it mean by the active regions? The active regions is when your L is equal to half wavelength. So this is in terms of the resonance. So the impedance offered by the dipoles are resistive, because you know that when resonance, as you can see that, usually you only have a resistive by the dipoles are resistive. Okay, and then elements currents are large. Okay, so because I is to V over R. Okay, so large and in phase. and in phase with base voltage, and then by the time field radiated from element In plus 1 reaches In, the phase of the In advances by 93 degrees and its field add to the field of In plus 1. In phase process, large electric field towards left. Hence, there is a strong radiations towards left in backward direction. So it means that for this, what we can see that usually for this active region, so if you have like this, the dipole here, so the radiation actually is come from here, backwards mean. So this is the in term of the active region. So if you talk about inactive region, we have L is less greater than lambda over 2. So we can say that dipole length larger than resonance length. So what we have here, the impedance become inductive, because if your L is less than lambda half wavelength, so we capacitive now it become inductive because of L is greater than half wavelength here, causing current to lag the base station, lagging the base station here. Let the base station, base voltage, sorry. Okay, this region presents large reactive impedance. So this region actually presents large reactive impedance to the line. So all the incident signal from active region is reflected back towards the back radiation. Okay, so it means that that's why you can see that in terms of the pattern. Okay, so this is your periodic. So you can see that, of course, you can see if this one is become reflective, so all the signal will be like this lah. So this is the radiations towards the backwards. Okay, right. So this is the three regions that exist in the log periodic types of antenna. Okay, now I would like to show you in terms of the design parameter for the log periodic dipole antenna. Okay, so okay, from the notes I have already shown you. Dalam notes ada, we have. So the most important thing here is, as we can see, that ln plus 1 over ln equal to, so that means that this is the length of the dipole. Rn plus 1 over Rn, the distance from the whatever dipole towards the apex angle, and Sn plus 1, the spacing between this, Dn, diameter of your your wire, or another things, An plus 1 over An. So this should be equal to 1 over tau. Where your tau here, where n here, I can say that where n is equal to 1, 2, 3, 4 up to, this is what is the number of elements. Okay, so tau actually is the periodicity, periodicity factor that can be design ratio or scale factor. Periodicity factor or scaling factor. Okay, so this is very important. And we have another important thing here is a spacing. Spacing for sigma. Okay, sigma actually is equal to Rn plus 1 minus Rn over 2 ln here. So it's equal to Sn over ln. So So what does it mean here? So if you have a two dipole here, so you have Rn here, and then you have Rn plus 1 here. So the difference between these actually is your Sn. This one minus 1 is over 2 ln. Ln is your this one. Okay, so this is what is this way. So this is the two important things in the log periodic types of antenna. The first one is your tau scaling factor, and the second one is your sigma spacing here. Okay, right. So let's say what is the apex angle here? Okay, let's say we want to find what is the apex angle. So this is your antenna here. So we have Ln. And then we have Ln plus 1 here. So of course, this one is Ln both. So this is your alpha over 2 here. Okay, so this one is the length of your dipole. So divide by 2 is NL over 2, Ln plus 1 over 2 here. Okay, and then this one is the same thing. As you can see that this is still alpha over 2, alpha over 2 as well. Okay, so this one actually is what? This length actually is equal to Ln plus 1 over 2 minus Ln over 2 here. Okay, so this is the spacing S here. So this is your N and N plus 1. Okay, so what we can see that from tangential, we know that tangent alpha over 2 actually is equal to Ln plus 1 over 2 minus Ln over 2 over S here. Okay, so this one actually is equal to Ln plus 1 minus Ln over 2S here. Okay, so from here, we can see that tangent alpha over 2 as well, it's equal to, you can just take out this Ln plus 1 over 2S, 1 minus Ln over Ln plus 1 here. Okay, so tangent alpha over 2 actually is equal to Ln plus 1 over 2S, 1 minus 1 over K. Let's say we say that this is just a K. K is a constant. K actually is equal to Ln plus 1 over Ln here. So in active region, we know that Ln plus 1 is actually lambda over 2 here. Okay, so what we have here, tangent alpha over 2 actually is equal to, so you must substitute to lambda over 4S here, 1 minus 1 over K here. Okay, so tangent alpha over 2 is equal to 1 minus tau over 4 S over lambda. We just take where tau actually is to 1 over K here. Therefore, we can say that your alpha over 2 actually is equal to arctangent 1 minus tau over 4 sigma here, where your S over lambda here actually is to spacing factor. Okay, right. Okay, so you got already the tangent, how you want to get the alpha tangent, alpha over 2. Okay. So the magnitude, we can say that the magnitude of log frequency period is found by the scaling factor, So we can say that log f2 over f1 is equal to log 1 over tau here, because f2 over f1 is to 1 over tau. F1 actually is equal to tau f2, and f2 should be greater than f1 here. And as well as we know that r1, r2 actually is equal to r2, r3 is equal to dot 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 rn over rn plus 1 actually is equal to tau, actually is to 1 over k here, is the same thing. And length of the dipole n1 over l2 actually is to l2 over l3 is equal to dot 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 nn over ln plus 1 is equal to tau as well. And Sn spacing over Sn is equal to k is to 1 over tau, and k should be greater than 1 and tau should be less than 1. Okay, so where your tau is a scaling factor, and usually a typical value of alpha usually is equal to 30, and tau actually is 0.7. So this is a value. And then the gain lies between 7.5 dB to 12 dB. Okay, so usually the values of tau lies between what, 0 to 1, and the input impedance lies between 50 to 100. So input impedance lies between 50 to 200 ohms. Okay, so this is a standard lah, what we can say here. So what we can also see here, what we can see as well in terms of the pattern. Okay, so the pattern will be in this way lah. So I can say this is your antenna here in this direction for H plane, and the same thing, the E direction is a bit more. So this is the E plane here. So this is a radiation pattern for the log periodic antenna. Okay, so this is what you call radiation pattern for LPDA antenna. And also we can say that in terms of the applications. Okay, so used in HF communication, where multi-beam steerable and fixed antennas are used, and then TV receptions, okay, or in terms of some monitorings. Okay, so advantage here, what we can say that to cover high frequency wideband antenna. Okay, so and then the radiation resistance and pattern do not depend on frequency. because that's why they call the frequency independent. Disadvantage, it's disadvantage is not suitable for low frequency. Okay, because of, as you know, that if you want to use at low frequency, example kilohertz and so on, so you need to have very huge dipole types of antenna. So again, usually typical value, I forgot to say here, typical value for your alpha usually is from 10 less than alpha less than 45. So that's why we use 30 degrees, or for the tau is 0.9 less than tau less than 0.7. Okay, so what we can see that if you have alpha reduced, then tau will be increased. This is a typical value. Okay, so I just explain to you. So this is your alpha. Because you put here 2 alpha or alpha over 2, it's okay. Because if you consider that one is an alpha, so you have to multiply it to get this alpha value. Okay, so what you can see here, this is a type of antenna in terms of the crisscross and as well as just a bit normal. Okay, so this is very important here. You see, Rn here, I just mentioned to you just now. So this is a spacing factor before the applications. And then this is the periodicity of the log periodics. Variations, okay. We repeat a cycle with the bandwidth of this. Okay, so this is a typical input impedance with the logarithmic. So this is what you can see that. Okay, so logarithmic input impedance variations. Typical VSWR. Okay, what you can say that this is your VSWR. So this is again a typical is about 7 to 8 dB, and then this is very so you can see that it's a very huge. If you talk about this one, what is the bandwidth? 1500 minus 50. Okay, so we have roughly about 1000 megahertz, for example. Okay, so this is again, and then this is alpha. I show you to you just now already, or sigma spacing factor. Lebih to lambda m2 and just shorter. In design, 1, 2 of the 3 parameters are specified. And then usually this is a standard lah, typical. As alpha increases, tau decreases. As alpha decreases, tau is increases. So this is the concepts that you should know. Large value of alpha or smaller values of tau results in more compact design requiring small number of elements separated by larger distances. In contrast, smaller values of alpha or larger values of tau require a larger number of elements that are closer together. For this design, there are more elements in the active regions which are nearly half wavelength. Therefore, the variation of impedance, etc., as a function of f are smaller because of the smoother transitions between the elements, and the gains are large. Okay, so this is a table to show the input resistance in ohm and directivities, dB above for the log periodic dipole. So what we can see here, when your tau is 0.81 with a resistance of 98, so what we can see that the alpha is about 15. Okay, so you can find out that your directivity is only 5 here, 65. Tau increase, okay, 0.89. So you can see that you have the same thing here, 9.8, and then tau is increasing to 0.95, so you can get higher directivity here. Okay, so this is just to show you in terms of, and also what is the design procedure that you need to use for this log periodic dipole array. So of course you need to find half angle here, alpha. Active region, so this is the active region as I mentioned to you, and then design bandwidth when you're active, your desired okay, BS actually is to be time BAR, active regions here. Okay, and then this is the total length of your log periodics, and this is the number of elements that you can use. Okay, so for the average characteristic impedance, as you can see that you can find some of this. And then mean relative spacing. So this is in terms of sigma over square root of your tau. center to center spacing of feed line is S to D cos Z0 over 120 here. Okay, so this is the plots that you can see in terms of the dB that you want. For example, contoh, for example, let's say if you want to have like 8 dB, so you just take whatever here, over here. So you can see that this is the optimum, your sigma. Okay, this is the sigma optimum, so you need to find what is the optimum, and then from there you can find what is the tau, and then you can find in terms of your sigma value. So once you have this particular value, so you can find in terms of this. And then this is the directivity that you can find if you know what is the theta in E plane as well as the H, so you can find the directivity of your log periodic dipole. Okay, so how you want to design? So I think this one, the design procedure, you should know how to design this log periodic dipole antenna here. Of course, usually if you want to design, you need to specify what is the directivity that you want to find. Okay, let's say for example, if you want to find 8 dB, okay, from the graph there, you can, you can get the value for the your sigma as well as whatever value just now. This one, you can find the tau as well as the sigma, spacing factor and tau here. Okay, right. Mana dia laju ni. And then from here, you can determine alpha. Okay. And then input impedance, real here, diameter of the element and feeder line, lower and upper frequencies of the bandwidth. Okay, so you can determine alpha, you can determine active regions here, and as well as the BS. BS is your values lah. Okay, so you put into here, and then you can find the L using this equation and N using these equations. So you can find, and then you can determine your impedance ZA using ZA is actually Z, and then you can determine Z0 over R in, and you can find your S using these equations. Okay, so this is the graph to show that relative characteristic impedance of dipole element or relative characteristic impedance of a feeder line versus relative characteristic impedance of the dipole elements. Okay, let's say you want to design this, because I expect that you can design this log periodic, you can design the Yagi-Uda, and you can design the helical for your assignments. I will give you the assignment before the semester break. For the first assignment, you need to design this kind using just a dipole types of antenna. Okay.